everybody. Good day. Today, I want to go over a concept in software engineering called composition. And what that means is essentially being able to create objects that are composed of other objects. So, as I have reached a milestone in my last project, one of the things that I like to do before moving to the next milestone is essentially clean things up a little bit to be able to look at how things could be made a little bit better to make the development process in the next phase easier. And so, in looking at my project that I am working on, I noticed that I had a couple of objects that have gotten really, really large. And when objects get really, really large, they get really, really difficult to work with. And this is a perfect spot, I think, to talk about composition in software development. So let's go ahead and dive in. This is mostly a theory type discussion meant to just instill or give you an idea of what composition is from a software engineering standpoint. You may already know some of this. Maybe you just need a refresher. Maybe you just want to hear my opinion. Or maybe you just have never heard of this before, and this might be something that could benefit you in your own development. Now, I will say that with composition, that this does not only deal with Unreal Engine development or Unity development. This is across the board a software engineering principle. So this can be applied to any type of coding at all. So composition in software engineering, what are we talking about? The first thing I want to look at are some what I call growth models. Now, growth models is kind of a term I've coined. Maybe I've read it somewhere and it sticks with me. But what we have here is an example of a controller and a character in a game, in an Unreal game. And this is actually my very example that I'm currently refactoring right now. And my class object has gotten very large. So what this graph is showing you is the left column here are lines of code, or how big the class is. And then these little areas inside are little domains that exist. Like these are the different responsibilities that these objects currently have. So you can see my controller, my player controller, is about 1,000 lines of code. And that's too much. And I'll go into that in a little bit. But 1,000 lines of code is already too much. And you can see this controller is responsible for 4 different things. It's responsible for some input content, some camera content, UI content, and pawns. And I also have a character class over here that's responsible for 4 different things. And this one's a little bit shorter. It's about 950 lines of code. But he's responsible for pawns, weapons, animations, and locations. So this all works. And I did a demo in my last video showing the game works. So it's not like the code doesn't work. But it could be better. It could be better for human beings to actually have to work on it and make our lives a little easier. Now, this right here is what I call a vertical growth model. And it's because it's tall. It's stacked up. This is in retrospect to a horizontal growth model. So you can see here on the right, this is the old scale, meaning my controller was 1,000 lines. You can break all of those pieces up into their own sub-objects, and they're a lot smaller. And you're going to have a lot more objects, though, underneath. So vertical and horizontal growth models. You may hear a term called a monolith. And the monolith is a carryover from older school development. And back in the 80s and the 90s, we used to develop applications as monoliths where the one application was just this one large thing called a monolith. And in that large application, you would have it doing all kinds of things. So the definition of a monolith would be a large application, a large class, or a large function that does not respect a domain and does many things. And when I say domain, I mean a thing it's responsible for, its domain. Is it responsible for logging? Well, then it should only be doing logging. If it's doing other things, it's not respecting its domain. It's crossing into other domains. Some examples I showed you, the controller class and the character class responsible for multiple different domains. Another example is a real life example I have where I've had to work on an application for a very large soft drink company who had actually two controller classes that were this big. One was 15,000 lines of code, and the other was 12,000 lines of code. And the 15,000 line of code class, one file, had 9 different domains and 4 different variations of how to deal with that domain inside of it. The problem with monoliths and why we don't like this is number one, it's difficult to troubleshoot due to its size. If you have to go into a 15,000 line text file to find out what's going on, even with debugging tools, it's not easy. It's quite painful in many cases. Second thing is it's difficult to maintain and extend. If you have to add on to that huge thing, you're going to have to know what are you breaking by adding what you're adding. What's not going to work any longer, and it's going to be hard to detect everything because it's just so big. And there's probably a lot of duplicated code inside of the functions. You'll have functions that are doing essentially the same thing as other functions, only slightly different. That can be painful. Good guideline, the larger your code in your class or your function, the more obtuse it becomes. So we want to keep these as small as possible. And a monolith favors vertical growth over horizontal. And that's the slide I showed you. It favors those large class objects. Now, the term composition in software engineering has been around for a while. It is a has-a relationship, meaning I have an object, it has this object, or it has a logging object. It has a controller object. But the application is made up of all those smaller pieces. This is different from inheritance, which is an is-a relationship. So an is-a relationship might be I have a person class. And from that person class, I create a soldier class, or I create a baker class, and they all inherit from person. So a soldier and a baker is a person. So we use inheritance for that. So these are two different concepts on how to design software in two different ways. Modern software will favor composition. You'll hear that quite a bit. If you're working for other companies and you have to do code reviews, you're going to see a lot of any type of inheritance you use might be nixed in favor for composition instead. And the reason that is given from an academic standpoint is that composition is easier to build out because it's more natural and it's more flexible than having to build out an entire family tree, which is what inheritance uses. That doesn't mean you don't use inheritance. That doesn't mean that inheritance doesn't have a place. They're tools that go in your toolbox. It's just that in software in general, we're going to favor composition over inheritance. Composition keeps your classes shorter. It keeps them more concise, which allows for a cleaner API, meaning I don't have to expose 50 public functions. I may only have 4 or 5. It's a lot easier to work with, both internally and externally as a calling client. Keeps your code within the domain focused on that domain. It allows me to change out a component with another component without breaking the rest of the client. And this one will favor horizontal growth over vertical. So you're going to have in a composition framework, which is what you're going to find in most modern software applications, a lot of smaller objects. So let's break that out visually. Visually, we have a car. So a car is an object, and I could, if I was coding a car in a game, put all my logic inside of that car object. But that would be bad. That would be a monolith. We see in real life that a car is composed of many smaller objects. So not only would I have a car object, I can have an engine, and that engine is composed of smaller objects. I have tires, I have head and tail lights, doors, instrument panels, and the interface that the driver uses to communicate with the car, such as its steering wheel and its pedals and its gear shifts. And all of those come together to form the overall car. So if I wanted to code this, each of those sub-objects would be its own class. Which, if I need to extend it, maybe I need to put in a better engine. I just create a better engine object and pop it into my car, and in theory, it should work. If I'm having a problem with tires, I know exactly which object to go look at, the tires object. I don't have to wade through the doors or the instrument panels or the engine objects or the code for that. I shouldn't anyway. I know that I've isolated a problem in the tires object, so I should be able to go into the tires object and deal exactly with that particular problem. So this is an example of taking a real life object and breaking it down into its composition. So when we talk about composition, we take ourselves to a very common set of design principles that you will find in software development in general. And we call those the solid principles. And if you're new to software development, this is a set of principles that I highly recommend you get familiar with and be able to explain. Because in a lot of job interviews, you're going to be asked to talk about this particular topic. This is one of the most popular interview topics that I have found in normal interviews that aren't something like Google or Microsoft, where they're probably going to ask you these questions anyway, but those will be your intros before you get into other things. Regardless of what level you're going into, solid principles are good for any software developer to understand. And there are 5, and solid is an acronym. Now, composition talks or touches 3 of these pretty heavily, so I'm going to talk about 3 of these. The most important or the most heavily touched is the S, and the S is single responsibility. And in single responsibility, that simply means a function or a class is responsible for doing just one thing. So if you have a class, it's going to have a domain, and it's going to stick with that domain. Anytime it has to do something logic-wise that doesn't deal with the domain it's supposed to sit in, you know you should break that into its own class or find the class that does that. If you have a function, that function should only do one thing. It shouldn't be doing multiple things. There's things that you can start to look at. The thing with development is a lot of it's opinion-based, and there are no hard and fast rules. People try to put hard and fast rules, but there's not. And you can go into the most strict code base and find functions that are doing 2 things instead of 1, for example. It just depends on what you're gaining from breaking out those tiny lines of code into their own functions. Like if you're making it bigger, if you're taking 1 line of code and extracting it out and forming 4 lines of code from it, because you have to create, the function signature and all that, it may not be worth doing that. So things you can look for. Functions, if they get bigger than your screen size, that's a good indication of you might want to break this out. It's probably doing more things than it needs to do. They call that a smell. So it starts to smell funny. So if you're doing a code review and you see a function exceed the length of a screen, that's you more than likely can break that out into something smaller. Classes, once a class starts to hit 400 or 500 lines of code, it starts to smell. It's probably doing some things that another class can handle. So you want to start looking for what those are and break those out. Not always. Sometimes you may get a class object that is 600 or 700 lines of code, and it's just that there's a lot of inputs and it's handling inputs. But you can probably refactor a few of those things in general to keep it around the 400 or 500 line mark. And 400 or 500 lines is just what I'm used to. It's not the absolute value, and it's not something I'm sure that some people could argue that it should be a different value. Some might say it should be 300 lines of code. And I've worked with those people, so I know that that's a thing. But in general, those are things you look for when your code starts to smell. How can I improve on it? Now, the I and the D in solid also deal with composition in some fashion. For my little demonstration, I'm not getting into these, but I'm pointing them out just because they're important to point out. The D stands for dependency inversion. And what that means is that the class object itself will, when it creates these composition objects or is dealing with these composition objects, it's not dealing with concrete versions of those objects. It's dealing with an abstract of that object. And how we get that to work is through interfaces. So instead of having an engine, for example, you're not going to create a new instance of engine. You're going to create a new instance of an I engine. And you'll have a factory class somewhere that'll produce that engine and send it back to you. And you won't care what the actual concrete implementation of that engine is. You'll only care about that it implements the engine interface, the iEngine interface. And that way you can swap objects out as you need, and it doesn't affect anything backwards compatibility-wise because it was only ever using an iEngine. It didn't care about the concrete class underneath it. Interface segregation is another important one. This one is often misused. So people understand interfaces are important. And in Unreal, you can even use interfaces, though it's their own special way of dealing with interfaces, which can be special. and I'm not going to talk about any of that in this video. That might be for another time. But so what they'll do is they'll say, okay, well, you said my engine has to, I need an engine interface. So that means I'm going to create the interface, and then I'm just going to expose all of the public methods to that interface. And now I've done the D. I've done dependency inversion. And technically, that's correct. You've done the D, but you violated the I, or potentially have violated the I. The I basically says don't show your clients more than they can see. And if you're dealing with an engine object, the key thing is what public methods or public functions in here does the outside world care about? Does a car care about? And only expose those. So your interfaces should be scoped directly to what its intent is. So an example in an Unreal game, you may have a hittable interface, an I hittable. And that I hittable may only contain one function called hit because it's scoped very, very closely to that particular domain, the domain of being able to be hit. And I can put that I hittable interface on a character class, and that character class could have 50 different public functions, but one of them is going to be hit. So when I'm dealing with an I hittable, it's the character class, but I only see the hit function because I'm dealing with an I hittable. Even though it's got 49 other functions, I don't care about those. I don't need to expose those to I hittable. And a character may have I movable, which are functions specifically for moving the character. Because I don't care if he can be hit, and I don't care if he can eat, and I don't care if he can sleep. I only care about all the things that it can move. So I can take those interfaces and just work specifically with those interfaces and not care about the rest. So interface segregation scope, it's a form of the single responsibility in a way. It's saying, keep this thing in the domain that it needs to be in. Don't create an interface that exposes every public method, because that's useless. Because that means when you create another I engine and it doesn't need a few of those functions, you're going to create dummy functions just to be okay with the interface, and they won't do anything, and that's useless. We don't do that. So in talking about all of this, you have to talk about over-engineering a little bit. Over-engineering is the extreme opposite end of not engineering enough or creating these monoliths. Over-engineering is to take a problem, solve for it in a very overly complicated manner. And this one will draw some heat because over-engineering, I think, is one of the biggest, the things I have seen more often in, I've been in tech and software development for, it'll be 30 years this summer. I've seen a lot of code. I've seen a lot of over-engineered code. Number one, it takes longer to over-engineer a problem because you have to think about all the different permutations you're going to create and then implement them all. So it just takes longer. Number two, maintaining and extending that code now becomes more difficult. If I've got 150 small objects, because I've gone 9 layers of abstraction, and you may think that that's a lot and I'm, over exaggerating. I'm not. I've seen an app. I had to work in an app that was 9 layers of abstraction, and it was very difficult to do anything in that application because it was just really difficult. And even the people who wrote it, who were very, very smart people, had trouble maintaining it. And it said, yeah, we probably wouldn't have done it this way if we could go back. The level of engineering you go to will depend on the team you're on and who's in charge of the code review process. So whoever the lead is or the architect will dictate how much you're going to over-engineer. Some people will want some, and I'm one of those. I would consider myself moderate. If I need to have a sub-object, I will create it. If I need to have like interfaces on everything, I'll put them. So my code, for example, I don't need interfaces right now. I have sub-objects that I've created to solve my problem, which we'll see here in the next slide. And I didn't put interface on them because I don't foresee swapping them out with things. I don't need to do any of that. And working with interfaces in Unreal is not the best. So because I don't need it, I did not do it. And when I do need it, I will then go back and do it. But for right now, trying to get code put out in a working manner, I don't see the benefit for me doing that other than to say I did it. And I require more than that from me. But there are teams that have worked on it where you would have to do that. You would have to break everything out in its own interface. because that would be the team standard. And again, it's all opinion based. It's all subjective, and it's going to depend on ultimately who's the one that is the one doing the code review and makes those rules for you. Again, this favors horizontal development. So over-engineering, I said, will bring a lot of heat just because some people may not consider something over-engineered where others will, and it really depends on you. So, but when you're doing your code, just keep that in mind. If you're making it so complicated, or you're adding features that you think will be used later but may not be used, you've essentially added dead code to your project, and you've just made it more complicated than it needs to be. So that being said, all that neat theory on composition. Composition, again, is taking an object and creating smaller sub-objects that it will interface with. That's composition. So looking at an actual example of composition, I have a player controller in my Unreal game. And that Unreal controller was 924 lines of code, which is too big. So I went through and I found all of its domains, and that's what these little sub-objects are. So I had input actions, unit orders, UI widgets, and camera pawn. These were all the things that the player controller was doing. So it's doing too much. So instead, what we have is, I'm saying my player controller should be responsible for input actions, and that's pretty much it. I want to take input from a user and do something with it. And I'm going to send the do something with it to a sub-object. So I took 924 lines of code and refactored that down to 524 lines of code, 400 lines smaller, and I created a UI bridge, a camera bridge, and a units bridge object that the controller creates on begin play. So now I have these 3 sub-objects that are part of my player controller, and they all together form the player controller. It's like Voltron, right? You know, if you know Voltron or Devastator from Transformers, the combiners, all the little Transformers combined to make Devastator. Well, that's this. All these little objects form to make the overall object. And when you're doing composition like this, the outside world, meaning other classes that aren't player controllers, when they interact here, they're not interacting directly with these sub-objects. They don't see those sub-objects. They don't care about those sub-objects. They can say, hey, player controller, I need you to update the user widget with the current health. And the player controller goes, cool, and has a function for that, and it tells the UI bridge to do that. So the outside world will never know that these objects exist. And the only logic that exists in player controller deals with anything that has to do with input actions. And that's it. If it has to do with implementing a UI or working with the UI, if it has to deal with moving my camera, if it has to deal with dealing with the units inside of my player controller, which are the pawns, there'll be a function that basically passes that through to those sub-objects. All right. So everyone, that's composition and software engineering. That's a 25-minute video. Thank you for getting this far. If you have any questions, feel free to leave them in the comment section. If you like this type of comment where I want to go over different software development tips, tools, advice, on top of just showing how my game development goes, subscribe and like the channel. That'd be awesome. And I appreciate you. But until next time, guys, I will talk to you later. Keep your code good, and we'll see you later.